Hello students, so today we'll go for the next concept of this amine complexes. So I have taken the ruthenium complexes here, okay, ruthenium 2 and ruthenium 3 complexes, and this is what the complex examine, okay. So this was been first observed by the Nakamoto, okay, Nakamoto, 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 he's scientist, okay, so researcher of the amine complexes of transition. So this is what, and the range he studied was from the 4000 to below 3000 per centimeter, okay, below 3000 per centimeter amine complexes in the far infrared, in the far IR region below 300 per centimeter, okay. And for these complexes, so you can see that the band assignment between 4000 to 650, assignment between 4000 to 650 per centimeter. So for this complexes which was been observed here, and you can see that the replacing the NH stretching vibrations was very easily resolvable, okay, NH stretching frequency here. And you can see for both the ruthenium 2 and ruthenium 3, so the chloride ions of boron trifluoride, okay, uh, fluoroborate salt, chloride, bromide, and chloride, okay, bromide, iodide, and fluoroborate salts of this ruthenium hexaamine trihalide X3 was been observed. And you can see that the complex, the NH3 rocking vibrations for these complexes was very sensitive, okay, NH rocking vibrations for these complexes, rocking vibrations, NH rocking vibrations for these complexes seems to be very sensitive here to change in the oxidation state of the central metal ion, okay. And for this the vibration for this the vibrations, so you can see vibrations frequency. So uh, this was in agreement with the spectra of examined complexes of cobalt 2 and cobalt 3, okay. So ruthenium complexes, and the color, as I said in the previous video, that the color, so you can see here these complexes of ruthenium 3 complexes, the color of the complex depends on the anion presence, and the fluoroborate is white in color. So this one fluoroborate complex of this ruthenium is white in color, and you can see the chloride complex of this is a little bit pale yellow, bromide is bright yellow in color, and the iodide salt is purple, okay, iodide salt will be in purple color complexes, okay. And here the NH3 symmetric deformation mode of this complexes is split in number of the bands here, okay. So this is what and I have shown one typical band here. You can see here three spectras of this ruthenium hexaamine Cl3 and ruthenium hexaamine Br3. This one, second one, this is Cl3, this is Br3. Then you can see this is third one, I3, and last one is BF341, like this, okay. Almost vibrations, two complexes, ruthenium 2 complexes, and of Cl3 type trihalide complexes, and which was been taken in the KBR, reported in the KBR, this complexes. And you can see that in this medium only one NH3 deformation band here. So you can see one NH3 deformation band you can observe here at 1313, here 1313, this is 1400, 1303. So this is what NH3 deformation band is observed, symmetric, okay. NH3 deformation symmetric is observed here, okay, at 1313 here, see, like this, okay, 1313 for these complexes, 1 2 3 4 complexes of these halide dihalides, okay, Br2, I2, Bf4 twice, and Cl twice, okay. So you can see here, and the splitting observed is been observed here, the metal nitrogen stretching vibrations, okay. So metal nitrogen stretching vibrations here. So metal to nitrogen stretching vibrations was expected to occur below 650 per centimeter, okay, for ruthenium 3, ruthenium 3 complexes below 650 metal to nitrogen, okay. So this is NH3 deformations symmetric stretching, and this metal to nitrogen stretching was expected to observe below 650 for ruthenium 3 complexes. Okay, RUN stretching, ruthenium nitrogen stretching vibrations. Okay, so although, but they were not observed but they are not observed for the fluoroborate BF4. So for BF4 they were not observed. Fluoroborate it was not observed. This is how we can, with the IR we can, it's a very helpful for the IR spectra for the complexes of the amine complex to determine the difference in the stretching frequencies and to identify the complexes. Okay, the corresponding band you can see here, ruthenium 2 were not observed here, so we have taken up to 1300 here, so 52 to 50 per centimeter. So even the weak band stretching at 4 to 37 per centimeter has to be, but it's not there here. We are not shown ruthenium nitrogen stretching vibrations, but in some they have reported. I have seen some papers, so it has been reported ruthenium nitrogen ruthenium nitrogen stretching vibrations for this. Okay, at 437 per centimeter, ruthenium nitrogen stretching frequency at 437 per centimeter. Some paper I have seen, they have reported here. So this is the highest but symmetric deformation stretching of NH3 has been observed in this case. Okay, and you can see that the complexes of this, which was reported, which was done at the scale of 4000 to 650 nanometer. So here the NH3 rocking vibrations, and you can see that the for one more complex I have taken here. So for this one, RuNH3CCl3 trihalide complexes, RuNH3 5 times dihalide complexes here like this. Okay, 6 times dihalide complexes you can see here, observed here. See the complex spectra is going to be observing in this way. So this is for ruthenium pentamine pentamine dichloride Cl2, then it is Br2 dibromide, pentamine ruthenium dibromide, and diiodide. Okay, are you, so you can see here, so this is for dichloride, dibromide, and diiodide complex. See, this is what for trihalide we can see here ruthenium amine complexes. Okay, and so here also you can see rocking NH3 rocking vibrations in the ligand, and it's more sensitive, and the frequency for these vibrations decreases here. So you can see the frequency of these vibrations decreases. So you can see here, so chloride is greater than bromide is greater than iodide here. The frequency you can see the decreases. That this is how the role of halide also is very much important here. So this is what we can see, and you can see that between 650 to 250. Okay, 650 to 250, okay, range for ruthenium nitrogen stretching vibrations, and ruthenium chloride stretch is expected to occur here. Okay, the metal bromine you can see here, and metal iodine. So metal bromine and metal iodine. Okay, so metal bromine and metal iodine stretching vibrations should occur at the lower frequency actually. Okay, lower frequency, and the strong sharp band you can see here at 301 per centimeter. So at 301 per centimeter, a strong band observed here, 301 per centimeter, around this one here, strong band 301 per centimeter for these complexes is because of ruthenium chloride stretch. So you can see here 301 ruthenium chloride stretch here. Okay, ruthenium chloride stretch here. Okay, and the other RUX stretching you can see vibrations beyond this range. Okay, other things, and 3 band attributed to ruthenium stretching here, nitrogen stretching vibrations assigned. Okay, and you can see the weak bands between 490 to 490, weak bands between 490 to 440. So we can see the weak bands we can observe here. So between 490 to 440% for this complex is chloride bromide, and this is how the band you can see 424 present here. And this also depends on the molecular symmetry also, C4V C3V in this way. Okay, so this is how we can identify with the geometry also, C3V C4V. So we can identify how they differ, the IR spectra differ for the same metal ion complex with different of the halides here. Okay, the main thing is here the ruthenium nitrogen stretching vibrations. So here also, so ruthenium nitrogen stretching vibrations. Okay, ruthenium nitrogen stretching vibrations, ruthenium nitrogen stretching vibrations. So they decrease in the order. So here chloride is greater than bromide, greater than iodide. Okay, so this is what. And this is how it is possible to present and assign the vibrations in the particular regions of these complexes. Okay, so this is how the most we can explain for the what you say the complexes, amine complexes, and the how the IR spectroscopy helps in identifying how they differ, the spectra, how they differ. See, the same ruthenium complexes is there, same ruthenium 3 complex is there, but how the IR differs here. So this is very much importance. Okay, here and here also we have seen one, here also we have seen. So how we the same complex for dihalides, how it differs here. So this is how the IR spectroscopy is becomes a very useful factor here to determine the complexes. Okay, so in the yesterday's class, in the yesterday's video, we have seen some of the complexes of iron complexes, and today video we have seen the ruthenium complexes of ruthenium 2 and ruthenium 3. Okay, so here we can come to know that how the IR spectroscopy is really helpful for determining the complexes. Okay, the shift in the spectra and all. So hope you understood this today. So because we require it to be learn this very slowly, because this is a new IR spectroscopy. In organic is very easily we can understand, but in organic complexes is a little bit you require time here, and we have to experience these spectras while we prepare the complexes. So we have to go for the spectras of this, and then it becomes very useful for us to understand, easy for us to understand the change in the IR vibrations. Okay, upon the bonding with the halides, as well as the change the vibrations between the metal and the ligands. Okay, so hope you understood this, and in the next class we will see that we'll go for the next this one, that is the pyridine. Okay, so we will take the another ligand pyridine, and we will see that how these upon binding with this, bonding with this metal and forming the complex, how the IR spectra is going to vary or going to differ in the next video. Thank you.